SLS is a super heavy rocket being created by NASA and is slated for its first launch in 2018. But that isn't the SLS we're talking about today. Instead, we're talking about the Space Launcher System family of launch vehicles designed by the US Air Force in the late 1950s and early 1960s, as a part of the Air Force's efforts towards landing a man on the moon, which was part of Project Lunex. The family consisted of highly modular 2- or 3-stage rockets, with either 1 or 2 core stages surrounded by 4 solid boosters. All of the SLS rockets would use segmented solid rocket boosters for the first stage. These boosters would come in 2 widths, a 100-inch wide version for the smaller rockets, and a 180-inch wide version for the larger rockets. The length of the boosters could have also been changed between launch vehicles by adding or removing segments. The second and third stage of all the rockets burned liquid hydrogen and liquid oxygen. These core stages came in 3 variants, A, B, and C. The A core was the smallest and would have used a single J2 engine. The J2 is the same engine that powered the second stage of the Saturn 1B and powered stages 2 and 3 of the Saturn V. The A core carried about 53 metric tons of fuel and had a burn time of a little over 4 minutes. The B core was much larger, but was more or less the same design. It had 2 J2 engines instead of 1, and carried almost 150 metric tons of fuel, with a burn time of 5 minutes and 45 seconds. The C core was the largest and would have used 2 M1 engines, with a burn time similar to that of the B core. The C core carried over 750 metric tons of fuel. The smallest rocket planned for the SLS family was the A410. It consisted of 4 100-inch solid boosters around an A-type core. The solid boosters would be lit on the ground and power the first 90 seconds of flight. Just before the boosters ran out of fuel, the core stage would ignite its engine, and the boosters would separate and fall back to Earth. The core would then continue on its way to orbit. This version would have carried about 9 metric tons to low Earth orbit and would have been used to test the re-entry vehicle for the Air Force's Lunex program. The next size up was the AB-825. This version used 4 180-inch wide boosters, which would power the flight for the first 100 seconds after launch. Just like the A410, the core would ignite just before the boosters ran out of fuel, but the AB-825 used a B core for the second stage. Once the B stage burned out, an A core third stage would light and finish the orbital insertion, or would send a payload to the moon. The AB-825 could send up to 39 metric tons to low Earth orbit, or almost 11 metric tons on a translunar trajectory. This would have been enough to send the Lunex re-entry vehicle on a flight around the moon in a mission similar to Apollo 8. The largest rocket designed as part of the SLS family was the BC-2720. It was almost identical in concept to the AB-825, but instead of a B-core second stage with an A-core third stage, it was a C-core second stage with a B-core third stage. Although the B-core third stage probably would have been modified to only use 1 J2 engine in order to increase payload to the moon. This version of the rocket probably would have also used solid rocket boosters with more segments to increase thrust and burn time for the first stage. The BC-2720 would have been able to carry just shy of 159 metric tons to low Earth orbit, and could send over 60 metric tons to the moon, much more than the Saturn V, which could only send about 48 metric tons to the moon. This version of SLS would have been used to bring humans to the surface of the moon. SLS was remarkably ahead of its time and had plenty of benefits over other more conventional rockets. At the time, liquid engines were still very unreliable. It was thought that by limiting the number of liquid-burning engines, these rockets would have higher success rates. The BC-2720 would have used only 3 liquid engines compared to the 11 engines used by the Saturn V. And by limiting the number of unique components between rockets, costs could have been greatly reduced. Using strap-on boosters for the first stage also allowed a reduced overall height, and eliminated the need for an inner stage between the first and second stages, which reduced weight. It also made hot staging possible, eliminating the need for a heavy ullage motor. Some of the smaller components, such as the A-core and 100-inch boosters, could have been transported via rail, which would have also reduced costs. SLS was also designed with a pure cargo version in mind in order to facilitate a permanent outpost on the moon. So why was SLS cancelled? Well, it was part of Project Lunex, which faced other problems, such as a complex landing vehicle which used the direct descent method of landing on the moon, and returned with a reusable glider similar to the space shuttle. This would have required more extensive development and research compared to the more conventional Apollo program. And when Project Lunex was cancelled, SLS died with it. In 1961, President Kennedy decided it would be NASA, not the Air Force, to bring Americans to the moon. SLS hasn't completely died, however. Many of the concepts were brought back to life with the space shuttle, and using strap-on solid boosters around a hydraulic core has become a common practice in rocketry. SLS influenced many rockets such as the Ariane 5, the H-2B, the space shuttle, the Delta IV medium, the Titan IV, and the modern SLS. So while the SLS rockets never themselves flew, many of their ideas did.
Control of land. Lattice now on the proper alignment for its 8.5.